Right, for example, P of 2 is equal to lambda to the power of 2 over 2 factorial e to the negative lambda. Now, which equal to 3 was originally in the equation 3 times P of 4. P of 4 is lambda to the power of 4 over 4 factorial e to the negative lambda. So on the left side of the equation is probability of 2, on the right side of the equation is probability of 4, and probability of 4 is multiplied by 3. The equation we're solving, and then realize e to the negative lambda is a positive factor, and that is a factor on the left side and on the right side. So we can divide e to the negative lambda from both sides of the equation, and then get rid of the exponent part. So then you have a lambda to the power 2 over 2. It is equal to lambda to the power 4 over 24 is 4 factorial. And I know that lambda is supposed to be a positive mean. It's an average number claim. Average number claim can never be 0. So we know for sure lambda is not 0. Therefore, this is a factor we should not consider since lambda is not 0. If it's a non-zero common factor, we divide it out of both sides of the equation. So if you divide lambda squared from both sides of the equation, then we will have, without the lambda square, we have 1 over 2. It is equal to lambda to the power 2, which is equal to did I forget the 3, right? I totally ignored the 3. I was supposed to multiply by 3 here. So there's this 3. There's this 3. 3 times probability of 4. All right, so then there's still 24. Right. Now we were able to solve for lambda. It's a positive lambda. Solve the rest. So far, all the answers submitted was correct. Any questions? This is trying to study if given the information of a situation, is it possible to find out the background, the underlying parameters? Right. Do you have any homework question? I reset all the dates of the homework, so they are due on the test day, which is Wednesday. We're in week 7. Today we're going to try to, I'll talk about any question that you might have. If you don't have questions, those I'm probably going to start 2.1. Questions. Right. Web work, all the homework. It's already reset, so if you have any leftover assignment, you can try to complete them. You can also try to look for a similar question to practice, the one that's similar to the test practice question. Last week we went over the test question. Actually, I loaded a class solution that we had earlier on Wednesday. So today, let's start a little bit on chapter 3. We're moving on to continuous distribution. So I have it. All right, chapter 3, we're gonna work on continuous distribution. Basically, in chapter 1, we have probability and how do we calculate probability value. What was some of the common probability rules? We have additional multiplication rule. We have 3 different ways to analyze a question. You can use a tree diagram. You can use Venn diagram. You can also use a table to display the sample space and to understand the information in the question. So and then in chapter 2, we look at overall distribution. So not just one single event. We look at any outcome. What is the probability for each outcome? And we can put it in a table, put it in the graph, or put it into a formula to calculate the probability. And then we have a couple of special distribution that's discrete. We have geometric distribution, hypergeometric distribution, binomial distribution, negative binomial distribution, Poisson distribution. So those are some of the frequently applied distribution. So in chapter 3, we're going to move on to continuous type. Continuous type is the kind of like the data value, the variable value are no longer discrete. They're continuous, so you can't single them out. So you cannot calculate probability of x equals 5 or probability of x equals 1 because they're continuous. If you focus on individual value, the probability is like almost 0. So for example, if you want to figure out how likely I drive to school and the probability the time is 10 minutes, right? So to be exactly 10 minutes, it's like try to control your action to the second, right? That's almost impossible. Very likely sometimes it's less than 10 minutes, sometimes it's more than 10 minutes. So if you find a time frame, like what is the probability is between 5 minutes and 15 minutes, that probably is very possible, like could be substantial. I mean, if the 10 minutes is roughly the average time. All right, so for continuous probability x equal to a single value is normally equal to 0. It's like the probability I drive to school and it takes me 10 minutes drive here, that probably is 0. Because to be 10 minutes on the dots is almost impossible, right? So 10.1, 10.01, that's more likely than exactly 10. To be exactly 10, we consider continuous since the data is continuous. We consider that probability as 0. And that's the difference between the continuous probability and discrete probability. If you are selling pizza, the probability of selling 5 pizza x equal to 5, it's very possible because many times you do sell 5 pizza, but for continuous data, for the variable equal to exact number, that's like almost 0. So we are not able to focus on the probability of a single value, and we tend to focus on the continuity of the information. All right. So now let's look at an actual question. I think I made 2 separate files. This is one's from exact text, and sometimes it gets to the point that it's very formularized, and then if you want to be accurate about it, and your wording has to be really formal. So this is a part the writing tends to be lengthy. All right, so we're gonna look at a couple of examples to actually understand how do we model continuous distribution. So we're no longer using a table, like, because if you only list them actually equal to 1, what is the probability x equal to 1? What is probability x equal to? What is probability x equal to? That's impossible. So we do not use a table because listing them one by one is impossible now. So we have 2 possible ways to display the distribution. Number 1, you can still use a graph, right? The graph is no longer it's no longer a histogram. Instead, it's actually a continuous curve. So we can have a rectangular shape or a horizontal line for your distribution. You can have a bell curve. You can have a triangular distribution. There are different shapes of the distribution. So they all when the sample size is large, it kind of look like the binomial histogram that we had in chapter 2. But if they're not, there's no step size, there's no discrete value. They're actually a smooth curve rather than one by one. So we have a couple of popular distribution that we are going to study. In chapter 3, we can start with uniform distribution is the most easy one. But then also that kind of made it a little rigid. And then we move on to other distributions such as exponential distribution, Bellman distribution, chi-square distribution. These are some of the very popular distribution, and these two are connected to the same model. That's why they are being related. They're being listed together. And then lastly is a normal distribution, which is frequency normal distribution is bell-shaped distribution. This is a distribution function. All right, so we're going to look at an example rather than start with the definition. So I'm going to start with this first question in the homework. All right, so this is a question about uniform distribution. It says a manager of a department store reports that the time of a customer on the second floor must wait for the elevator have a uniform distribution ranging from 2 to 4 minutes. So this is a waiting time. Suppose you're on the second floor. You're push on the button and wait for the elevator to come up. So the waiting time can be from 2 minutes to 4 minutes. If it takes the elevator 15 seconds to go on, I wish I hadn't put this one at the first question. What is the probability that the hurriedest customer can reach the first floor in less than 3.5 minutes? Floor to floor. That should be the first question on the uniform distribution. I thought I have rearranged them. Well, let's start with this question. So I find that the actual information about running time at 15 seconds that kind of messed up, made it less elementary. All right, let's start with this question. This is a question about waiting time for a loan application to be processed. So as you can see, all these questions, the waiting for the elevator or waiting for the loan application to process, all relate to about waiting time. I mean, in real life, there are actually a lot of waiting time which kind of making this model a little bit more applicable. But as you can see, you have to apply it to something that's kind of uniform. So there cannot be any high intensity point. It has to be like about the same. So like this question, when you submit a loan application, your waiting time can be anywhere from 8 to 16 days. So that's equally likely 8 or 9 or 10, definitely a little bit over a week. So you can kind of setting up a what's called a density curve. You can set up a graph to try to visualize what's going on. And that graph is what we call a density function. Now, the question says waiting time is anywhere between 8 to 16 days, equally likely and uniform. That's the thing about uniform distribution because they're equally likely. So when you set up try to draw a curve, you will be writing your information about the days, which is a random variable that's called x. It's anywhere from 8 to 16. All right, so over here we have, suppose this is 8 days, and this is 16 days. Now, because it's equally likely, we will have a horizontal line for it. So how high is the line? So then we're really trying to draw a rectangle here. So the length of the rectangle from 8 to 16, 16 minus 8 is 8. So length is 8. So how do we determine how high we want to? We are trying to draw a horizontal line, right? Draw horizontal line. The height of the line has to make it possible so that the entire area below this line equal to 1. Because in a continuous distribution graphic display, we want the area below the curve to equal to 1. So suppose you're trying to determine the height here. This height has to make the entire area below this line between 8 to 16. This rectangle I'm drawing, it has to have an area equal to 1. Area equal to 1 means that's the total probability of 1. So then the height here must be 1 over 8, right? 1 over 8. So this is 1 over 8. Okay. So that is really this line, this horizontal line is what we are calling the density curve. And then area below the density curve represents the probability. So we're trying to use this as an example to get familiar with the term and notation. The term, the density function. The graph here is the graph here is called the density curve, and the probability below the curve, the shaded area, is probability equal to 1. Now the question says we want to find probability that X is a low application days, waiting days, probability that X is longer than 9. So we're trying to find P of probability that X is higher than 9. All right, you can write higher or equal, having it equal or not having it equal. For continuous distribution, it's the same thing because X equal to 9 have a probability of 0. So we don't have to write an equal sign there because equals probably X equal to 9. It's a probability of 0. So what we're looking at, we're going to identify the 9. So we're going to try to find on the number line, because it's between 8 to 16, 9 is like roughly here, a little over 9. So we want to know what is the probability to be over 9. As you can see, if the total probability is between 8 and 16, to be higher than 9 is very likely, right? So if you submit an application, it will tell you anywhere from 8 to 16. So you're like, oh, very likely it's going to be more than 9 days, right? Right? To be exactly 8 days or a little over 8 days will be, you got to be really lucky to be like less than 9, right? So to be higher than 9. And so the look of it is that the area below the curve higher than 9 is a big portion of what's going on. So the calculation of that is actually a division. That is a division between the part and total. Your total distance is really 16 minus 8 because the range is from 8 to 16. Now the range for the interval we are looking at is 9 to 16, right? When you see higher than 9, but in default in the uniform distribution, then 9 will be a lower bound, the 16 will be the upper bound, right? You might want to go to 17, but it's impossible to try to stop that from happening. In real life, that's not actually. You have to talk to the bank. They may tell you it's between 8 to 16, but it's possible it's 17 days because real life data, nobody gonna stop the model from being not the model. Right, 8 to 16. So the numerator will be 16 minus 9 because the lower bound is 9, upper bound is 16 in the model, if the model is true. So we have a probability of 7 over 8. And that's a question. That's the answer to the question. Probability X bigger than that is 7 over 8. Any question? All right, so this question, I think I should move this one to the question number 1 because that's a more likely a basic question you applying uniform distribution. Now I want to use this one as an example. That is when you are trying to describe a uniform distribution, the visual presentation of the density curve look like this. All right, the one that we had at 8 to 16, but in a general uniform distribution, the x value is in a lower bound to upper bound, calling that A and B. So the height of the curve is 1 over, remember we have 1 over 8, and this is 1 over 16 minus 8, 1 over 8. right? And the density curve is 0 otherwise, meaning that even though we just draw that part, but all the other part, you can consider them have 0 value. That's why they're not visible in the picture, but they're actually considered 0. So if you define it this way, your density curve is being defined for all real number, not just A to B, but it's actually defined for all the other number as well. So that's the density curve. And we have to guarantee that area below the density curve equal to 1. That's the probability of 1. Any question? All right, and another thing is what is the probability? And we cannot calculate probability of all of them. So we're putting a construction called a cumulative probability. So what is the probability x is below the probability below x, right? So that is called f of x, which is the cumulative distribution function. This is a probability density function. This is a cumulative distribution function. So we will have probability x is below a, and then as we were calculating, it's going to be a fraction. The denominator is highest number minus the lowest number. Now the numerator is in your probability model. To find probability x is between probability the random variable is between x and a. It is a higher value minus a lower value as well in the numerator. So that is the fraction that we are calculating in the example. This is the one we did. We did 16 minus 9 because 9 is a lower value, and then x, which is 16, is the highest value. So that's calculated. All right, so we're able to construct 2 different functions. For continuous distribution, you have to have the formula for your density function, the formula for your f of x, for your cumulative distribution function, which we call them CDF. And we gotta have the formula for the mean, formula for the variance, and formula for the moment generating function. So for any distribution, we wish to have all of them constructed. All right, so I only have the density function. So if you look at the cumulative distribution function, because the higher the x, the more likely the probability it's going to be an increasing function. So after we calculate it, it looks like this. As a cumulative distribution function, this is density function. Essentially, the cumulative distribution function is area below the curve. So you go x equal to lower than a, probability 0. X equal to here, this is the probability. X equal to here, this is the probability. Let's get here, and probably get higher and higher. If x is over here, then this is the whole area below a, so it's probably 1. So x is higher than b, the probability 1. So this ends up being the probability ends up being a continuous function, and it's the area below the curve. Area below any curve can be calculated as an integral. So f of x is actually the integration from negative infinity to a of the density function. So essentially, this function's derivative is this function, and this is a integration of this function. So between the density function and the cumulative distribution function, there are derivative of the CDF is the PDF. Integration of the PDF is the PDF. So they have that calculus relation. Integration, and you can write it in the integration format if you're calculating CDF. You can write it in differentiation form if you are trying to figure out the density. Any question? It can be confirmed by this. So if you try to find the derivative, see the slope, so that's the slope, and then therefore slope is the derivative of a function is a slope of the tangent line. So this part has a derivative of this constant slope. Okay. And then over here is horizontal, so it has a slope of 0. Over here it has horizontal, so slope equal to 0. That's why this 2n has slope of 0. This one has a positive slope. That's how it looks like for the CDF and PDF of the uniform distribution. Question? All right, so basically the entire section 1 focuses on uniform distribution. It also is an opportunity for us to understand what is a cumulative distribution function looks like. It looks like, well, let's talk about the common property and differences between the cumulative distribution function and the discrete distribution and the continuous distribution. For continuous distribution, one of the things we have to study is the density function. Right, so what is density function? Density function is like the counterpart of a probability formula in the discrete distribution. In the discrete distribution, we have probability mass function, which normally called f of x. F of x represents probability x, the random variable equal to x. All right, so similar to the probability in the discrete case, the density function has to be a positive function. And as well, by definition, it cannot have negative value. If it does have negative value, that's not well defined. Number two, if you try to find area below a density function, which is calculated by integration, so integrating the density function from on the entire domain of the function, it will equal to 1. So that is really area below the density function equal to 1. Lastly, if you are calculating probability that random variable is between A and B, this probability can be calculated by integration. And that's different from the discrete case. In the discrete case, if you want to find probability x is between some number, you're going to calculate them one by one and add it together. So the probability calculation in the discrete case is a finite sum. The probability in the continuous case is a continuous sum. Remember, the integration notation is an elongated S, right? Summation, continuous sum, and that's the similarity and differences between the continuous case and discrete case. These are the three properties for density functions. Many of them we should start remembering them. You got a distribution function. You want to calculate probability. Now, very likely you have to integrate. So, and here we have to revise, review, refresh integration technique. So many times the difficulty in some of the continuous case calculation is in the difficulty of integration. Yeah. For that, we have the function calculator tool. So you can use some online calculator to help you integrate if you have a hard time integrating the function. All right, let's move on to the CDF, which is a cumulative distribution function. And that's the probability. That's really a probability for x to be below the value, below the variable. So to calculate probability, as we mentioned in continuous case, when you want to calculate probability, you're supposed to do integration. So this is a function that's defined by a variable integration limit, integrating the density function. All right, but most of the time, if the function is integrable, it's some words. Integratable, even a valid English word. If this one can be calculated, use appropriate antiderivative, we'll have a function formula, so we don't have to keep it in the integration format. And then we might have an easy time for the probability calculation. Remember earlier we said you got to calculate probability for continuous case, you have to do integration. But if you already have the CDF and the integration is already done, you can just take the formula and then plug in a number. That's already a probability. All right. So those are some of the definitions for the continuous case. This is a general. This is not just for the uniform distribution. This applies to all distribution of continuous type. All right. And then let's talk about how we calculate. This is for the uniform distribution. Well, what does it mean for uniform distribution? What is the variance? And what is the moment general function for the uniform distribution? So this should be calculated using a formula. I think this is the solution. This is the mean, the variance, and this is the moment general function. And this actually needs a little bit. Should actually go over from the text since I didn't really have that part here. All right, so this is how we were being presented in the book. This is a CDF, and you can see that it's the integration of the density function. This is the comparison between the two forms. About the calculation part, example, it doesn't really give us the calculation. All right, this is one of the exercises behind the section. I guess we were lead to calculate all these values for ourselves. I guess I should try that. And a little exercise. All right, for uniform distribution, we have these three results. You remember, for any distribution, we wish to be able to know their mean, their variance, and their homogeneous functions. So how do we calculate the mean? Suppose you have a uniform distribution, which is defined by f of x equal to 1 over b minus a. And that's when x is between a and b. Suppose a is a smaller number. It is otherwise defined as 0, so we don't have to worry about the other values. It's a piecewise defined function. Now, how do we calculate the mean? All right, mu equal to expectation of x. Right. Now, remember, calculation. Did we not mention this? Calculation of the expectation is a integration. Right, so the mean of the continuous distribution, the mean is calculated by an integration as well. The mean is the x value multiplied by the density function integrated. In discrete case, the mean is calculated by a finite sum. You have the data value times the probability and add it all together. That was a discrete case. For continuous case, we have data value times the density, and then we integrate it rather than add it together. So it's calculation for the expectation. Calculation of variance is equal to x minus the mean squared and then multiplied by probability and then integrated on this domain. And that's the calculation of variance. So following that formula, let's look at how do we calculate this. We were supposed to integrate from negative infinity to positive infinity. However, the density function is 0 otherwise, and only have a non-zero number between a and b. So our integration will be from a to b. We were supposed to take the x value times the probability of x dx. So this is a formula for calculating the expectation. So now we have from a to b, x is multiplied by f of x, which is 1 over b minus a. Right, that's 1 over b minus a dx. Now for integration, if you have a constant number, normally we bring the constant number outside the integration. So become 1 over b minus a, and that's integration a to b x dx. For integrating integration of function, this is a derivative. So the calculation of the antiderivative is what function has that derivative. According to the power rule, this is power 1. 1 plus 1 is 2, right? Integration raised the power, so x to the power 2 over 2 will be the antiderivative. And we were supposed to calculate it from a to b. Right. This part is the integration process. So you integrate this, you have this, and the coefficient 1 over b minus a is still there as a fraction. All right, so this is equal to, we're going to plug in a and b, so 1 over b minus a. If you plug in b, it's b squared over 2. Now, if you plug in a, it's a squared over 2. Right, that's how it looks like. They are both over 2, so the calculation goes is equal to 1 over b minus a. So it's going to be b squared minus a squared over 2. So this is equal to actually b plus a times b minus a. Right. This is equal to b squared minus a squared, right? Right. That's the numerator. Denominator is going to be 2 times b minus a. So you can see the b minus a is a common factor. Cancel the common factor. We have b plus a over 2, or a plus b over 2. That verifies that the mean equal to a plus b over 2. So that's the first verification. So we prove the first equation. The second equation is calculation of the variance. The variance is equal to expectation of x squared minus the expectation squared. We already have the expectation, so we have to calculate expectation of x squared. this is something we have to work on. Again, whenever you want to calculate expectation for the continuous case, is the integration. So we're going to integrate a to b, and then this is a x squared dx. Now x squared times f of x is 1 over b minus a dx. So we're going through the same process as there, except that one was x times 1 over b minus a. This is x squared 1 over b minus a. All right, and then again, this can be getting out of here. So we have the integration that goes 1 over b minus a. Integration, then we have x squared dx. If you finish integrating this, is 1 over b minus a. All right, this integration is a similar process. So that one has x squared over 2. Since we're integrating x cubed, this is going to integrating x squared, so it's going to be x to the power 3 over 3, right? Right. So this is going to be x cubed minus, well, plug in b and a. This is a and b. So it's going to be x cubed over 3, but plug in b, plug in a, so it's going to be b cubed minus a cubed over 3. Kind of like this, okay? Except we have power 3, 3, 3, 3. This become this, right? And then we can find a common factor. This one you can factor b minus a times b squared plus a squared plus ab. So after cancel the b minus a, there's a b minus here, there's b minus c here. After cancel the b minus a, we have this. Goes 3, so it's a squared plus ab plus b squared. That's after we cancel b minus a. That's this part. Okay. All right, so then let's finish the calculation. So this is equal to a squared plus ab plus b squared over 3. Minus b plus a over 2 squared. All right, if we square, it's going to be 2 squared is 4, and this is b squared plus a squared. I'm trying to get closer, we're trying to verify that. This is equal to, since the denominator suppose this is the denominator 3, that's the denominator 4, right? The common denominator will be 12. Also, we switch it to 12, so it's going to be 12, and they all times 4, so it's going to be 4a squared plus 4ab plus 4b squared. First one, second one is minus. We have 12. Now we have to times 3, so it's 3. And this is b squared plus 2ab. Plus a squared. That is square of the numerator square, the denominator times 3 both, and then we subtract. After subtract the 4a squared minus 3a squared, we have a squared. 4b squared minus 3b squared, we have a b squared. And then 4ab minus 6ab, that gives us negative 2ab. Which confirm this is exactly the same as this after we cancel the common terms. Any question? So the calculation of the green part altogether confirm the variance equal to b minus a squared over 12. The moment general function is another expectation. So I have to do another integration. I believe it was following the integration of the exponential function. And you can see this as really the e to power minus e to the power over b minus a, right? That's the exponential function. I think we're able to do that by ourselves. We're just integrating the exponential function. Any question? Just try to confirm the uniform integration part. Right, so hopefully this gives us some confidence moving forward. let me leave that one because I'm still iffy on the, it takes the elevator 15 seconds to go. And let me finish the other assignment. We'll try to spend a little bit more time on that. So this is question number 2. Again, I feel like this is a standard question. X is a random variable. It has a uniform probability, and the values from 2 to 5. So 2 is a A, 5 is a B. So if you want to find the probability density function, it's 1 over B minus B over equals 1 over 3, right? Like 5 over 5 minus 2, it's a 3, and that is a. All right, that's this one. If x is between A and B, then the f of x, the density is 1 over B minus A. All the other value is 0. 0 everywhere else, except if it's between A and B. This is question 1, and part B is the mean, which is if the value is uniformly between 2 to 5, and then the middle, which is the middle of 2 and 5, 2 plus 5 is 7, 3.5. So the mean is 3.5. And then we're doing B plus A divided by 2. 5 plus 2 divided by 2. 2.5. And the standard deviation is supposed to be the square root of the variance. What was the square root? The variance. The variance is equal to, for uniform distribution, the variance B minus A squared over 12. That's the variance. If you take square root, it's going to be B minus A, because we're square rooted, right? So it's B minus A over root of 12, right? Over root of 12. So we'll take B minus A over root of 12. B minus A is 3, so 3 divided by square root of 12. That's the variance. Any questions so far? And these are the ones that we're able to answer with our formula. Question number 2. Right, the last 2, let's say, if we draw a picture, it makes more sense. So we have 2 here and 5 here. It's horizontal between 2 and 5. Therefore, the height is 1/3. Right. This question is, what is the probability x is between mean plus the standard deviation and mean minus the standard deviation? Now I need to know the number for the standard deviation. For standard deviation is 0.866, so I'm taking that number. We calculate it. So mean is at 3.5. So this is really a probability that x is between 3.5 plus 0.866. Okay, and this side is 3.5 minus 0.866. That's the probability. The calculation will be whenever we calculate uniform distribution, the overall length is supposed to be the total. And then you take this part a little bit above and a little bit below is this part, right? Since it's uniform, the denominator should be 5 minus 2. The numerator should be this number minus this number, right? Right. We subtract. Then there'll be 3.5 plus standard deviation minus 3.5 minus the standard deviation, which essentially the entire length is going to be 1 standard deviation, 2 standard deviation. Really, is a 2 standard deviation. So like 2 standard deviation there. And this is a standard deviation right there. So answer the question will be over 3. What was the numerator? 2 times standard deviation. So we'll time this time 2. It was 3 over square root of 12. If you time 2, it's going to be 6 over the square root of 12, right? And 6 over square root of 12 divided by 3 is going to be 2 over square root of 12, since that's a division. Are we okay? All right, so the answer will be 2 over square root of 12. 2 over 12. This question. All right, the last one is easier because you just want to find what is the probability is higher than 2.7, 2.17. So this is a 2.17. We want it to be higher, which is all that, right? higher than 2.17. So the denominator is 5 minus 2. This is between 5 and 2. The numerator is going to be the lower bound, this is the upper bound, half bound minus the lower bound. So 5 minus 2.17. That's all we need to calculate there. Subtraction, that's the calculation here. So for the last one, divided by 3, and here we're going to go 5 minus 2.17. The last question. So this is number 2. Any question? So this, as long as we have the formula for the mean and formula for the standard deviation, the rest of them, we know the value and we can find the upper boundary and lower boundary. Question 3 is a uniform distribution between 1 and 5, and we're finding the probability. A makes the following probability. All right, this is a backward guess. You might have to do a little bit of solving because these are the kind of question we have the probability. We're trying to find the boundary for that probability. So this is the number 3. We got a uniform distribution between 1 and 5. That's 4. So the height is 1/4. 5 minus 1 is 4. That's the distribution. The first question is, what is the probability that x is less than a has a probability of 0.05? That's the question. So now in that case, this number is a probability, so it must be a ratio, right? Ratio between the part and total. So the denominator is still going to be the 5 minus 1. The numerator is going to be this. We're looking for the a, right? We're looking for x less than a. So a is right here. A is here. So the probability x lower than a is 0.05, right? So this is probably going to be upper boundary is a, so it's a minus 1 equal to 0.05. Solving that will give us the a, right? Okay, there. Do you solve equation that is 0.05 a equal to a minus 1/4. Multiply both by 4, then you have 0.2 equal to a minus 1. Therefore, a equal to 1.2. So that's question 1.2. And so with similar reasoning, let's say the second question is the probability x lower than a. Oh, well, they're pretty much the same. Remember, I was saying equal or not equal, the same thing. So this difference between the two questions is at 0.14 and that's 0.05. So the second question, all you have to do is 0.14 equal to a minus 1/5 minus 1. To calculate it, this is really a minus 1/4. So multiply 4, you have 0.56 is a minus 1. So a equal to 1.56. The answer is 1.56. These two are very similar, so you have very similar calculation. The difference is when I switch the angle, but then this is x higher than a. If this is a to be higher than a, we're looking at this, right? So lower bound is a, upper bound is 5. So in that case, you will do the probability is 0.44. So the upper bound is 5, lower bound is a. 5 minus a equal to 5 minus 1. The overall, the big difference is 5 minus 1, and this is 5 and a is the lower bound. So that ratio should be 0.44. That means the probability for x higher than a, this is a, be higher than a on the right side. And then we finish the calculation, and now we'll get the a part. Are we okay? All right, last question is the probability between a and 1.14. In that case, you will be setting up an equation kind of like 0.38. That's a probability, therefore it's a ratio. The denominator is 5 minus 1 as well. The numerator is a upper bound minus lower bound. So the numerator should be a minus 1.48. That equal to this ratio. Again, instead of this equation, you're solving for the a. Once we finish a, you get that boundary. Just really solving for the upper boundary. So all five have very similar reasoning when you try to determine the value of the a. It's really finding the value of a. The a makes it upper boundary, makes a lower boundary. The a also that's also an upper boundary. As long as it's a uniform distribution, the calculation is always upper boundary minus lower boundary divided by the upper boundary minus lower boundary for the overall population. Any question? So this is a backward calculation. Before we got a boundary, we calculate probability. This question is we got a probability. Let's find the boundary, one of the boundary of the interval. What is the calculation? This is when we did it. This one is uniform distribution between 15 and 35. What is probably above 28? What is probably between 17 and 25? So that would be 25 minus 17 divided by 35 minus 15. As long as you got the boundary right, that division will give you. The expected temperature should be right between the upper bound and the lower bound. So we have 35 plus 15, which is 50. So it must be 25. That's the expected temperature. When you say expected, you're calculating the mean. Anything else? All right, the rest of the calculation, you have to understand that the calculation probability is integration of the density function. So this is an integration question. And this, so you got a probability, and sometimes the probability question is that the density or a CDF. It's a CDF. So if you have x equal to, if you integrate the density function, well, this function already is integration. We are trying to find the case, so the function will be well defined. So a CDF is supposed to be an increasing function. The highest value of the function is highest value of the function equal to 1. That's when x equal to infinity. We're determining the k. Normally, I would consider determining the k using the formula that we had in the text. That's integration of the density function from negative infinity to positive infinity should equal to 1. And then since f of x have a k, we can use this equation to solve for the k. This one we get a cumulative distribution function. All right, let's try that. I feel like this is question number 7. The first question is to determine appropriate constants. And then we'll calculate the mean. Of course, calculation of the mean will be integration of the x times the density. This is finding the probability, which is calculating the probability, using the formula. Calculate probability will be integration question. So this is the question that was mentioning. Let's get the first question calculated, and then we'll try the other question if we have time. All right, so this is a CDF. And again, the derivative of CDF is a density function. So if we differentiate it, C f of x is equal to derivative of capital F, which is equal to, differentiate this, we'll get negative k times negative 3 is 3k And then the x raised to the power of -4 differentiation. All right, this only works for x is higher than 46,000 and 0 elsewhere. All right, so according to our definition, the integration of this function will equal 1. Okay, so it's a 0 everywhere else, so there's no need to integrate below 46,000. So we integrate 46,000 to infinity of the f of x dx, which is supposed to equal 1. This is according to our requirement for any density function. So for any density function, you integrate it from on its domain, it equal to 1, and that will allow us to solve for k. In my head, I was trying to think, can we just solve it from here? But just work it out using the density function. So we will integrate it as 3k, which is coefficient. So bring the 3k outside. Then we have x to the -4 power dx. I differentiate it and then we integrate it. I feel like I'm doing some unnecessary extra work. There must be a quicker way to get to this equation. So this equation, this calculation can be done and then we solve the k from here. Obviously, k is really large. That's why the question itself wants us to find the logarithm. So we have 3k multiplied by, if we finish integrating x to the -4, the power is -4 according to the power rule of the integration. Power plus 1 divided by the power, right? So it's going to be x to the power of -3 divided by -3. That's the antiderivative. You can also try to find the derivative of it. If you differentiate this, is -3 to the power negative, which go back here, right? So we can guarantee that the derivative of this function is that function. So integration is a inverse operation of differentiation. And we're going to plug in upper limit, lower limit. Upper limit is infinity, lower limit is 46,000. Which equal to 1. Now, if you plug in you plug in infinity to the power -3 because the power is negative, it's reciprocal, right? So it's like a 1 over infinity, which is equal to 0. So at the upper limit, it's actually a limit value, and that is at that equal to 0. So 0 minus 46,000 to the negative power. Okay, so this is going to be 3k over -3. So then we have 0 minus the 46,000 to the power of -3. Okay. Since this 0 minus something that makes a negative number times negative number, that's a positive number. Also, this 3 in the numerator cancels 3 in the denominator. That's k times this equal to 1. So what's k equal to? And so k times, the 3 is already canceled, the negative also cancels. 3 times 46,000 to the power of -3 equal 1. So then k is equal to 1 over 46,000 to the power of -3. And negative power in the denominator become positive power, so they equal to 46,000 to the power of positive 3 if it's no longer. Negative on negative, they cancel the power, the negative side. That's the k. Question itself wanted a logarithm of the k, natural log of k, because k is really large. So if you take natural log of k, you're taking natural log of 46,000 to the 3 power 3, so it's 3 logarithm 46,000. So even if after we take the natural log, it's still pretty large, but not as large. So 3 times logarithm of 46,000. That's the answer to the first question. Any questions? I don't know if we plug in infinity will work out. But I did a little bit back and forth between the operation and differentiated and then integrated back to make a equal equation. All right, so this is a part A question. And this should be some of the common theme. Whenever there's a constant number, there's a number that we don't know. We have to apply the integration. This is really the key. Integration of the density function equal 1. That's what we are applying. There are similar things. The rest of them are just applying the formula. You're going to calculate the mean. You have to integrate you have to integrate the density function. You have a density function right here. You multiply this by x and integrate from 46,000 to infinity. It's a similar process. Let's see, if you have difficulty, we'll come back to it. A similar process here, but this one we have the density. So this density integrate from 0 to 3, which equal to 1. That allows you to solve for the k. All right, and this question has no unknown number. If you want to find the probability x is bigger than 30, you have to integrate 30 to lower bound is 16, lower than 16 to infinity, all right? So if you want to calculate probability x is bigger than 30, you have to integrate from 30 to infinity. You're integrating this function to get that probability. So in continuous case, probability calculation become integration question. And then this cumulative distribution function will be integration of these as well. Right. So you can see as we added to move on to the continuous case, the question can be a little bit difficult. Let's go back to question number 1 since I skip it first. The question is not hard. Computation wise, it's not hard. It's a concept of why we're doing certain things. So let's read this question one more time. So basically, the waiting time is uniform distribution between 2 to 4. If it takes an elevator 15 seconds to go from floor to floor, find the probability a hurry customer can reach the first floor in less than 3.25 minutes after pushing the elevator button on the second floor. Let's see if we're able to get it right. Basically, we're calculating probably the random variable is waiting time. Reach the first floor in less than 3.25 minutes. I realize it's not the same question. Takes the elevator 15 seconds to go from floor to floor. That's the elevator's time. Find the probability that customer reached the first floor. So we want to find the time the customer reached the first floor, not the waiting time, right? The waiting time is a different time than the customer reached the first floor time. We wait for the elevator. Doesn't mean we're already in the first floor, right? You wait for the elevator and you get here, and then you have to get on the elevator to get to the first floor. So after this customer pushed the button, and then this person is waiting for the elevator. It takes the elevator to it takes 2 to 4 minutes to get to the elevator. After the customer get on the elevator, it takes the elevator 15 seconds to go from second floor to the first floor. So that's 15 seconds more, right? So we will have to add 15. So if we think about the time, it's like 2 different time. One is the wait for the elevator's waiting time. So this is a time to waits for elevator. All right, and then Y is the time to reach first floor. They're not the same time, but we can see they're pretty close because it takes only 15 seconds to go from floor to floor. So roughly, maybe I can see that Y is equal to X plus 15 seconds, which is how many minutes? 1.25. 0.25, yeah, 0.25 minutes, 50 seconds, a quarter of a minute, right? So that's the relation between the two times. So we're calculating probability that Y is less than 3.25. All right, and then because Y equal to X plus 0.25, we're actually calculating X, which equal to probability that X is less than 3. That's all we need, right? You have to take 0.25 minutes to go down that floor after you got the elevator, but you have to wait for the elevator. You're waiting for the elevator. It has to be less than 3 minutes in that case. Now we can go back to the original question. Now the waiting time, which is X, is actually between 2 to 4. So this calculation is going to be equal to, not be back to the smaller fonts. So equal to the denominator is 4 minus 2. Then the numerator, what happened there? Let me just go ahead and write it. It will put it in the appropriate place when I want it to. All right, so the numerator is going to be like this is a 2, this is a 4, and then we have 1/2 here. And we want the waiting time to be lower than 3. So this is a 3. 3 is right in the middle, right? So it looks like the probability is 1/2. So numerator is going to be 3 minus 2. That's what it is, right? Below 3, but definitely over 2 since the waiting time is limited between 2. So that the numerator is going to be 3 minus 3 is equal to 1, 4 minus 3 is equal to 2. So this is really 1/2 the answer to the question. All right. So as you can see, the discussion is more than the question solving. We added complexity is we realize we're talking about 2 different times. As long as we can understand the relation between the 2 times, we should be able to convert it to a general, a uniform distribution question. Right. I feel like when we are doing the entire assignment for the first section, the main difficulty is all those integrations. So if we are a little bit rusty calculation of the integral, then we might have to go back and look at our notes on the integration formula. All right, that's pretty much all for today. But remember, we have a test coming up on Wednesday. Have a formula card ready if you need one, and use the practice questions to help you prepare. All right, I will see you on Wednesday.